start the class. Please take your paper. This paper, as I told you, it is mainly focused on hydrostatic section. I told you up to now that this is 11th topic, 11th paper, 11th model paper that we all are doing. So in 11th paper, I thought of help you in lot to understand the fluid static section. So let us discuss, right? Let us discuss. These are some complicated questions, especially these are some difficult question, I must say, related to the hydrostatic or the fluid static. I'll start one by one and we will discuss each and every question here. Yes, it is difficult. I know that's difficult, but don't worry. Once we discuss, you will fully understood. I don't think there will be an issue. So nothing to worry. I'll try my best to explain the most important part in these questions. Right. Let's start with the first question. Question number 1. Relative density of a mixture of water and alcohol is 0.8. Relative density of mixture of water and alcohol is 0.8. They have given the relative density of alcohol as 0.75. If the volume change occurring during mixing is negligible, small, volume, ratio in mixing alcohol and water is. Right. What is this question? What they asked from us? This is model paper number 11. Let's say, as I told you, we can take a small table. This is the mass, this is the volume, and that must be the density. Right? This is alcohol. This is alcohol. This is water, and that is the mixture. Right? They have given to us the relative density of alcohol as 0.75. 0.75, you can say 0.75 gram per cubic centimeter, right? Easily we can get that way. Water, it is 1, right? Water is 1. They ask you, and the relative density of mixture is 0.8, or you can say 0.8 gram per cubic centimeter, because when you take the relative density, you can simply convert into gram per cubic centimeter without multiplying any value. So you just take gram per cubic centimeter. Let's say the volume of that would be V1, which we mix. Volume of that would be V2. So this is V1 plus V2, isn't it? V1 plus V2, because they tell there is no volume change in the mixture. There's no volume change in the mixture, right? Since the mass is equal to the volume into density, we take it as 0.75 V1. We take it as 1 V2, 1 into V2, right? Let's say it is actually M1 plus M2, 0.75 V1 plus V2. That's the total mass of the mixture. Right. Now you can do what? You can say that relative density of the mixture is equal to 0.8, which is equal to total mass 0.75 V1 V2 divided by V1 plus V2. If you go with the density of that, it tells you mass divided by the volume. Mass divided by the volume. So what they want us, V1 over V2. The volume ratio mixing alcohol and water is alcohol and water, V1 over V2. They want you to find V1 over V2. Here 0.8. You can multiply here V1 plus V2 equal 0.75 V1 plus V2. Just divide all the terms by V2. 0.8 V1, 0.8 V2 must be equal to 0.75 V1, that is equal to V2. Take this one to here, it is 0.05 V1. Take this one to here, you get 0.2 V2. V1 over V2 then equal 0.2 divided by 0.05. It is like 20 divided by 5, 4 to 1. 4 to 1 ratio is maintained, right? I told you how to do this kind of question. Draw a small table, then it is easy, right? It is easy. Shall I move to the second question, or you want more time to write this one? These are much complicated questions under the fluid static section. Okay, let us move to the second question of this. Let us move to the second question of that. Water is filled up to height 0.1 meter, that means 10 centimeter, into a beaker of cross-section area 80 square centimeter, is kept on a balance and shown in the figure. It gives the reading 0.820 kg. Then the finger is dipped into water until the water level rises up height 0.01 meter. Reading of the balance now is right. So actually at this instant, what reading tells you the total weight of water plus the vessel. Are you clear with that? So when the system is kept like that, this particular reading tells you the total weight of water plus the vessel. I hope everyone could understand that. When you dip your finger or the hand into the system, into water, there is an upthrust on your hand or the fingers. There's an upthrust on it. Definitely there's an upthrust, right? Because of that upthrust, the liquid need to be displaced. Actually, what happens when you dip your fingers to this system, what you could see, the water level rises to a certain value. Now it is here. Now it is rises up to that level. It is given as what? It is given as 0.001 meter. 0.001 meter, or else you can say 0.1 centimeter. 0.1 centimeter. Okay. So that is the upthrust develop on your fingers. That's the upthrust develop on your fingers. I'm telling you, similar type of upthrust would develop onto this water, because action and reaction forces are there. Similar upthrust would develop into water, into this water. So let us say that that is U dash. U dash must be equal the liquid displaced, the weight of the liquid displaced. It is volume into density into G. What is that? V rho G. V rho W G. V is what? Cross section into the height. Cross section is given as 80 square centimeter. Let's convert into it's given 0.008. Cross section into height 0.001. Rho W, which is 10 to the power 3 into 10. That is the upthrust develop onto the fingers. Same upthrust develop on the water. When you simplify that, what kind of answer you get? 8, 10 to the power minus 6, 10 to the power 4, which is it is minus 2, 0.08 Newton. 0.08 Newton is the upthrust, right? Upthrust. What they asked, the new reading. Initially, it was what? New reading is, let's say R dash. The new reading is R dash. Initially, it was 0.820 kilogram. Now, apart from the total weight of the system, the upthrust would apply on it. Upthrust is what? You need to divide by 10 to convert it to kilogram. So it is 0.008 kilogram. What is the answer? 0.828 kg. It's the answer. It is the reading now in the scale. Okay, next. I hope everyone could understand. So this is the way that he used the fingers. Definitely there's an upthrust. That upthrust develop on the fingers as well as the upthrust to develop on the water. Action and reaction forces. For the fingers, it should be like that, towards upward. Same force should apply on the water. Let's move to the third question. Question number 3. Two immiscible liquids. Immiscible means they are not mixed together. Two immiscible liquids of density D1 and D2. They have given us D1 greater than D2 is present in a beaker. Two immiscible liquids. This is D1 liquid. This is D2 liquid. D1 and that must be D2. A solid sphere of uniform density D is completely submerged, and floating inside it. So that 3/4 of its volume is submerged in the lower density. If I take the total volume of that as V. This particular volume is what? 3V by 4. Then this volume is what? We get V by 4. V by 4. Value of D is given by the density of this liquid is given as B. So we have done this kind of similar type of question when we discuss the theory. We know that the total weight of this object is balanced by upthrust. One is this, another one is that. Let's say U1, U2. There are two upthrust values which balance the weight of the object. U1 plus U2 must be equal to total weight. You can write like U1 plus U2 must be equal to the mg. What is U1 here? What is U1? It is volume density into G. What is U2? Volume density into G. V1, sorry, 3V by 2, 3V by 4, volume B1, D1, G plus B by 4, D2, G must be equal to mg. Must be equal to mg. G cancel. 3V by 4, D1, V D2 by 4. Instead of mass, I'll be taking that as volume into density. Volume is V, density is V. V cancel. You just multiplied all the terms by what they want from us to find the value of D. So let's take 4 here. 4 equals 3D1 plus D2 equal to D. That's the answer. Fourth one is the answer for that question. Not difficult actually. Not difficult. Let's move to question number 4. An ice block is completely immersed inside water using a thin string as in the figure. When the ice block melts, water level inside the beaker. So forget about this. If you don't use a string, what kind of observation you have, you may notice this ice cube should come to the liquid surface and definitely it will float. It will float. That is our observation, isn't it? You observe that if the string is not there, the object reach to the liquid surface and float. So if the ice cube fully melt at this situation, what happened to the liquid level? Will it change? That won't change. We have learned that. That won't change, right? Actually, what they have done, they have purposely take this volume into the system, into water, inside the liquid. At that point, there is more upthrust on it. The upthrust must be developed up to that level. Up to that level. Once it's fully melted, nothing would happen, only the liquid level would drop. Right? This liquid level should drop there. Because we know that it's fully melted, nothing would happen. But purposely take to the top, what somewhere here, definitely the liquid level should drop. This need to be dropped. Understood? Clear? Yes or no? Right. Yes. What happened? Drops down. Answer is number 2. Answer is number 2. Right? Remember, when ice cube float on water, liquid level won't change. But here, the purposely they take inside the water. So what happens? There's a water displaced, there's a liquid displaced which is equal to this particular volume. Once it's melted, nothing would happen. This upthrust or this displaced water need to come to inside. Okay, let's move on to question number 5. Don't do kind of like a mathematical questions. You can't do like that. Even if it's MCQ, you need to use a small logic to get the final answers. Not difficult. One end of a uniform rod is pivoted, hinged to a wall of a container as in the figure. Other end is immersed in water. The rod can freely rotate along the horizontal axis going through the hinge. So this is the horizontal axis it has. Through this axis, this can be rotated. This can be rotated through this axis, horizontal axis. At equilibrium, exactly half of the rod is inside water. At equilibrium, exactly half of the rod is inside water. Relative density of the material of the rod is relative density of the material of the rod is. So this is water. This is water. Let's say the density of that is rho W. This is the density of the material is rho. If you take this particular rod, we can mark forces on it. One is the weight of that rod. Let's say it is mg. Another one is the upthrust on it. Upthrust on it, which is the center of ions and center of gravity. This is the center of ions and this is the center of gravity. Right? Center of ions and center of gravity. Okay. So here, let me to mark the distance. Here, the total length of the rod is, let's say, 2L. The total length of the rod is 2L. Okay. If that is 2L, this must be L. Ne? This must be L. Right? This must be L. That small section is L. If the rod length is 2L. Okay. And the next thing is they tells us the half of the actually if that is L, this liquid surface need to be exactly go through the center of gravity, isn't it? It should go through the center of gravity because the half of the length is inside the water. No, it should go through the center of gravity. Did you get my point, every one of you? Okay, ne? Right. Here that is this is L. This portion is this from here to there we have L. Then it must be L by 2. This part is L by 2. Okay, I will mark that as L by 2 here. L by 2. L by 2. So let us take this one as theta. This one as theta. This angle is theta. So somebody can take this length or the distance as L cos theta. L cos theta. Here from here to there, this length can be taken as what? This length can be taken as L plus L by 2. L by 2 cos theta. Now we can take the moment about this location. Let's say location A. This is like discussing the question. So I do some kind of exaggerated way, but don't think that it will take this much of time to complete the question. We will take the moment about point A, sigma tau about point A must be equal to 0 because the system is now in equilibrium. The rod is in equilibrium. You can simply say the clockwise moment must be equal to anti-clockwise moment. Mg multiplied by L cos theta. Mg L cos theta must be equal to Mg L cos theta must be equal to upthrust into L plus L by 2 means 3L by 2 cos theta. Cos theta cancels. Mg L U into 3L by 2. L cancel. 2Mg equal 3U. 2Mg. Mg is what? Volume into density. Let's say the cross section of the rod is A. Total length of the rod is 2L. Volume into density. Rho. Volume into density. Cross section into the length is the volume. Volume into density. Into G must be equal 3 upthrust. Upthrust is what? Cross section into L into rho W into G. V rho G. G cancel. Even AL cancel. Now you have 4 rho. In the other side you have 3 rho W. 4 rho divided by rho W means 3 by 4. 3 by 4. Understood? It is the fourth one. Always remember, if you are taking the moment from a point like this, if you have only the vertical forces, how did the 3L come? 3L comes with this one. L plus L by 2. When you simplify 3L by 2, isn't it? Okay. Right. when you take only the vertical forces and no need to take the theta here, we realize the same L and 3L by 2 you can take without any problem because the cos theta cancels in both sides. Since these are MCQs, you need to do like that. Remember, no need. Since we don't have any horizontal forces, no only vertical forces. If the horizontal forces are only axis, you can do the same thing, right? Yeah, that's good. That's fine. If you haven't used the theta, that's good. Right. Let us move to question number 6. Question number 6. A liquid is filled into a tall tube closed at one end so that an air bubble is trapped at the end of the tube is sealed. So we have a kind of a tube, tall tube, and we have a liquid inside it. Here we have a air bubble and this also sealed now. This point also sealed. This opening also sealed. There is a air column, air volume. Now the tube is inverted and air bubble is now moving up along the tube. Now you inverted it. When you inverted it, what happened? Initially there was air, but now it is go through it and try to come to this location. Right? Now it is go through it. Let's consider that air bubble is now moving up along the liquid. Moving up along the liquid. Why the air bubble is moving up along the liquid? For the air bubble, there are two forces. One is the mg of that, and other one is the upthrust of it. Upthrust is more than the mg, that is why it's moving up, isn't it? For the air bubble, the weight is very, very small, right? But it has certain volume, so the upthrust would develop. Because of the upthrust moving up, isn't it? Because of the upthrust moving up, upthrust is more than the mg. That's why it's moving up. Okay. Now the tube is inverted and the air bubble is moving up along the tube. Vertically held tube is now released from rest to fall under gravity. Then the air bubble. When it is fall under gravity, what happened to the upthrust? Do we have an upthrust on that instant? So when the system is falling under gravity, what happened to the upthrust? Upthrust is missing. We don't have an upthrust at that situation, right? We don't have an upthrust. So remember, at that situation, the upthrust is not there. If you don't have an upthrust, what happened? There is no extra force. There is no extra force to move up. What happened? This remains stationary. Remain stationary with respect to the liquid. System is moving down. System is moving down. That's a different case. With that, the liquid, with respect to the liquid, it is stationary and all are traveling with the gravitational acceleration. So it doesn't move through the liquid. That is the first part. First one, let's read the answers. Move up more faster than the liquid, wrong. Move up through the liquid as previous, no. Move very slowly through the liquid, no. Doesn't move through the liquid, yes. Stop and then move down through the liquid, no. Wrong. Doesn't move through the liquid. Understood? Right. So everything we have given as a note, no, I'm not trying to give the note here because we have done that part under the note, right? Question number 7. Let's move to question number 7. A solid hemispherical object of weight W is immersed in a liquid of density rho using a spring as shown in the diagram. If the tension of the spring is T and the cross-section area of the flat surface of hemispherical object is A, Recognize the net force exerted by the liquid on the curved surface of hemispherical object is. Right. Let's mark the forces. One is the tension force which apply on the hemispherical object through the spring. And other one is the upthrust. Other one is the upthrust. The other one is the weight of that object, which is capital W. Capital W. And we know that these forces would apply perpendicular. I mean, these pressures are applied perpendicular to the given surfaces, right? Perpendicular to the given surfaces. Okay, perpendicular to the given surfaces. So if you want, you can resolve this horizontal and vertical. We realize horizontal forces are neutralized in both directions. So the resultant is not there horizontally. Only the vertical forces are left. Actually, we can simply say that for the curved surface, there is only vertical force. There's only vertical force. Let's say it is FC to say that curved surface. FC. Downward force, FC. And from the bottom, we have another force because of the pressure. We have another force because of the pressure. The pressure is H rho G into capital A. Let's say it is F dash. H rho G into capital A is the force that developed from the bottom to bottom surface. So for this system, you may have several forces. One is the T, other one is the upward force, which is F dash. Other one is the downward force on the curved surface. Other one is its own weight. Mg or W. So sometimes you might feel that what happened to the upthrust? Actually, the upthrust is developed because of this force and that force difference. The upthrust is developed because of the pressure differences and their respective areas. No need to take the upthrust again because it developed from the pressures. Okay, clear? Right. Here we can take the equilibrium of this object. So we can say that T plus F dash must be equal to W plus F. T plus F dash is H rho Ga W plus F. So F equal T plus H rho Ga minus W. That is the force which develop on the curved surface. Fourth one is the answer for that question. Fourth one is the answer. Okay, right. Let us move to question number 8. Let's move to question number 8. Question number 8. Density of water is 1000 and density of ice is 900 kg per cubic meter. The minimum volume that an ice block should possess so that the bird of mass 2 kg can sit on the ice block without sinking. We know that the ice cube would float on water. Ice float on water, right? So at that point, you can simply say that the weight of the ice cube must be equal to the upthrust on it. The density of water is 10 to the power 3 rho W. Rho ice, it is 900. So now what they try to do, there's a bird which is on the ice cube, so it is fully immersed. There's a bird on the ice cube. Now it is fully immersed. Here, there's a new upthrust. On it. Let's say U dash. The new weight M plus 2 into G. Okay. I hope everyone could understand. They want us to find the volume of the ice cube, minimum volume of that ice block, so that object, the bird of 2 kg, can sit on the ice block. We can write the equation U must be equal to the mg first instant. U must be equal to the mg. What is U here? It is U equal. We can write that U equal V rho G. This volume is V1, this volume is V2, or else we can say the total volume is V and the immersed volume is V1. V1 rho Wg equal V rho ice G. V is the total volume, rho ice G. G cancel, V1 rho W, V rho ice. V rho ice. That's the first equation. Okay, that is the first equation. In the second, V1 is, we don't know actually, but we can say 900 V1, no, 1000, 10 to the power 3, rho W, sorry, V1 must be equal V for the 900 V1, 900 V, let's say number 1. In the second instance, we can say that U dash must be equal to M plus 2 into G. What is U dash? It is volume rho W G M plus 2 into G. Here V rho W 10 to the power 3, G cancel, M plus 2, M plus 2, M plus 2. Ten to the power 3 V equal M plus 2. So here we can they want us to find the total volume, right? Even we don't want this one to find the answer. Here, look at this point. 10 to the power 3V must be equal. Instead of M, we can write mass into density. 900V plus 2. Because mass of the ice cube equal 900 into the volume of that. 900 is the density into volume. Here 100V must be equal to V equal 2 divided by 100. V equal 2 10 to the power minus 2 cubic meter. It's the answer. 2, that means 50. 1 over 50 answer is given based on that. No, second one is the answer. Actually, we don't want this particular part, even though we discuss it, we don't want it. Easily we can get the answer from the second section. Right. A small vessel is floating in water, inside water, in another vessel as in the figure. An object with a density higher than water is kept inside small vessel as in the figure number B and figure number C. Same object is immersed in water outside the small vessel. If heights of the water level are H1 and H2 and H3, they are relationships. Right. I will come to this. So they want you to comment related to the H1, H2, and H3. Right. I will start with this. When you take, when whatever the situation, if the vessel, if this small vessel go inside the liquid would displace more. That's the simple story, isn't it? This is a small vessel and this is a big one. If go inside the liquid, if go inside the large vessel, definitely from these two sides, the liquid would displace more, right? So they are, when I compare with those two, definitely this H2 is more than H1. Why I am telling like that? Because of this object, the liquid would displace more. There's an upthrust on it. There's an upthrust on this block, on this object. You don't want to think about these vessels. The reason is all instant the vessels are the same. So no need to comment. Based on the objects only, we can comment. Here we have an upthrust which is equal to the weight of that. Let's say the weight is 500 Newton. So you may have an upthrust. You may have an upthrust which is equal to 500 Newton. Definitely, what we know, one thing, H2 is greater than H1. That's a definite case, right? Or else H3 is greater than H1. In the second instance, this object is taken out and go through the liquid. Now it is here. There is also upthrust. Let's say the new upthrust on that is U dash. If the U dash is 500 or less than 500, less than, exactly, it is less than 500, like 200 Newton. So at that situation, you need to know that the upthrust is not 500 now, it is 200. So liquid would not displace that much value. So here H3 is more than H1 but less than H2. Understood me? Here it is H2 is the largest, then H3, then H1. This is the relationship. I think my question paper, you need to correct it. Second question, second answer, make it H2, H3, H1. Right? Right. Okay. Let's move to question number 10. Right, let us move to the question. Question number 10. A piece of ice of constant thickness is floating on water so that 1 centimeter of it is present above the water level. If densities of ice and seawater are 920 and 130, respectively, the total thickness of the ice block is. Here we can say that we have two forces, one is the upthrust, another one is the weight of this ice cube. We can write the equation. Let's say the total thickness is x, so it is x minus 1. We can write the equation upthrust must be equal to the weight of the ice cube. Upthrust equal cross section into x, ax. Cross section into a into x, ax. Cross section is a. We have uniform cross section ax. It is the volume. V rho g. equal the mass of the ice cube, total volume is AX. I'm sorry, I should make it as AX minus 1. It is not fully immersed, no. X minus 1. AX rho ice G. G cancel. A cancel. Always don't worry. You take unknowns. They would definitely cancel. X minus 1 into rho equal X rho ice. X minus 1 or X minus 1 rho, it is 920, sorry, 1030 X rho ice 920. It is cancelled. 103X, 103, 92X. Take it to this side, or take it to this side, yes. We have 3, that is 8. No, this is 1, 11 equal 103. 11x equal 103. X equal what? 10, 11. You would get the answer like 6.2. Is that 6.2? Anyone else? It is 9, right? 9. We get 9 something, né? It should be 9 something, 9.3, I suppose. 99, no, 99, that is 4, we don't have. 440, that is 33. Yes, let's take number 4 as the answer. Number 4 as the answer. Okay, we'll move on to question number 11 now. Question number 11. As in the diagram, a vessel filled with a liquid of density ρ1 is kept on a balanced piece of metal of mass m, and density ρ2 is immersed completely in water using the string without touching the wall of the container. Now, if the string is cut, change of the reading of the string balance is. Right, I will do this one. Look at here. So at this point, you may have a certain weight of this vessel plus water. Let's say it is W, right? So in the reading, you may it is indicated like R1. R1 must be the composition of W plus U. Why I'm telling like that? For this object, there's an upthrust. The same upthrust should apply on water. So the reading is given by the total weight of the system. System means water plus the vessel. W plus U. Understood? W plus U. Yes or no? Right. In the second situation, what happened? Now this block, they cut the spring. So this block touched with the ground or the bottom surface of it. Look at here, I'm trying to mark the forces. At this point, there's a weight of that mj, and the normal reaction would apply on it. Normal reaction would apply on it, and the upthrust would apply here U, and the upthrust would apply on the liquid also. Right? And apart from that, the total weight of the system is applied. Total weight means W. Total weight means I consider only the water and the vessel. Apart from that, there's a normal reaction for the object as well as there's a normal reaction for the vessel also. When it is touched with the bottom surface, there is no tension force. This is the whole section. This reading gives the whole section of that. When you take the whole section, Lamai, upthrust cancel. Normal reaction cancel. Mg plus W only left. So the second reading is only W plus Mg. Did you get my point? W plus Mg. Because now this, when you keep on top of the scale, definitely it shows you the total weight of the system, total system weight. It is W plus Mg, but I just want to mark the normal reaction values, and I wanted to show that how they cancel out. Okay, W plus Mg. So the difference of the two readings here, R2 minus R1. R2 minus R1, W plus Mg minus W plus U. W plus Mg minus W minus U. W cancel, Mg minus U. What is the upthrust? V rho G. V rho G. V rho G. The mass of the object is given. It is we can say that it is V. According to them, the density of that is given. Density of the liquid is rho 1. The density of the object is rho 2. The mass of the object is, we can write volume into density rho 2. G minus V rho 1 G. V G we can take out. No. We have to keep that Mg. We will keep that as Mg because in the answers, when you look at the answers, Mg is there. Mg minus V, instead of volume of the object, I substitute density of the object divided by the, instead of the volume, I substitute mass divided by the density of the object. Rho 1 J. Check whether you got my point. The volume of the object is now replaced with its mass and the density. Got it now? Right. You got it, right? In front of you. Right. Now we can take the Mg out. When you take Mg out, we get the exact answer that they are given as the answers. Second one is the answer for that question. When they touch the two surfaces, within the touching surfaces, the forces are developed now. So when you keep a certain mass on my hand, the forces are developed on the object as well as the forces are developed on my hand, isn't it? The same thing is there. But when I consider the whole system, they are cancelled. No need to think about that. So sometimes you might ask me, why did I consider this? Why didn't I consider as the whole object? Then I should consider this ring also, which is not possible for me to discuss. In that case, I forget about the object and consider only the vessel and water. But here, now I can completely consider that as a closed object, closed system, because it is inside the vessel and touch with that. No tension. Understood? We will move to the question number 12. Look at question number 12. Right. The diagram shows a mercury barometer. The point is the mercury column at which the pressure is 500 millimeter of Hg. Right. It is a mercury barometer. If it is a mercury barometer, what is the pressure here? It's a vacuum. No pressure. I hope everyone could understand that part first. If it is a mercury barometer, this is question number 12. Mercury barometer, No pressure, no pressure here. Why? It's a vacuum, no pressure. From here to there, we have a height difference of 760. 760 means if you take the middle point, it is like 380. From here to there, we have 380 millimeter of mercury. So if somebody asks me, what is the pressure here? I would say that it is 380 millimeter G or Hg millimeter. Understood? Clear? 380 millimeter Hg millimeter, right? So that means this is not the, this point is not the answer. Somewhere here means it's like 500 Hg centimeter. From here to there we have 760. So in between those two locations we have the answer. What is the point? It looks like what? C, ne? Looks like C. Right. Let us move to the question number 13. Question number 13. A thin polythene bag, thin, right? It's a very important term. Thin polythene bag containing 10 to the power minus 4 cubic meter of water with no air bubbles. Inside is tied by a light string and lowered into a bath of water as in the figure. If the density of water is 10 to the power 3, the tension in the string is. Very simple question. If you could catch that point, what is that? The tension they want us here. There are three forces now. One is the tension, another one is the mg, another one is the upthrust. These are the three forces which apply on the system for polythene plus water inside it. What we can say about the upthrust and the mg of this, assuming there is no mass for the polythene bag, you can take that assumption. Why? Because they have given that as a thin polythene bag. Thin, it's not a thick one, thin one. Yes or no? What is the value of upthrust and mg? If I say they are just equal, can you understand that? Yeah, that is equal. The reason is the weight is exactly equal to the upthrust. Upthrust means the weight of the liquid displaced. We have a water volume inside it. The same amount of volume would displace there, right? Same amount of water volume would be displaced. So when you multiply it by the density, we get the mass here. So upthrust and mg both are same. What is the value of the tension then? What is the value of the tension? Zero, no tension. Forget about that. Let's say this is mercury. That's mercury. What happened at that point? Mg is very larger than the upthrust because we have very high density. Mg is very larger than the upthrust. So you need to take the difference to find the tension. Okay, right. Think about that. Let us move to question number 14. And if this liquid having a lower density, it never come to the bottom, it come to the top, like it's floating. At that moment, the tension may be not there, right? You need to hang it in a different position, not like it the same way that we did here. Question number 14. The given J tube has a both ends scale and contain a liquid of density rho The broad arm has twice the cross-section area of that of the narrow arm. If P1 and P2 are the pressures of the trapped air, P1 is equal to. What we can say about the pressures in the both locations? They are equal. Why? We know that for a given homogeneous liquid or the stationary fluid, horizontal places, we have the same pressures. We maintain the same pressures in a horizontal plane. So that tells us the pressure here and the pressure, they are the same. You can say that P1 is equal to P2 plus H rho G. P2 plus H rho G. P2 plus H rho G is the answer. Second one. Very simple. Let's move to question number 15. Question number 15. A piece of coke is tied to the bottom of a container of water by a light inextensible spring as shown in the figure. When the container is moved horizontally to the left with a constant acceleration, which of the following diagram best represents the change observed in the water surface and the direction of the spring? Right? Direction of the spring. I don't think that you have a doubt related to the how this water meniscus is placed. When the liquid vessel is taken horizontally towards the left, it is how it happened. I think that is not a problem. The problem arises what is the position of the coke? That is your question. So let me to explain that. Forget about the coke, right? Let me to take a small liquid volume. Let's say the mass of that portion is simple m. The volume is v, and we need to take that water particle. Let's say the volume is m. So the mass is m. And there's a force from this side because of the pressure F1. There's a force from this side that is because of the pressure. Here you can say that this is height H2 and that is height H1. Simply you can say that F2 must be equal to H2 rho G capital A. If I want, you can exactly say that what is A here? A is the cross section of the sphere. I mean, we know that when you cut it, what kind of area it is there. I discussed that on the theory, how the forces are developed based on the pressures for these curved surfaces. It is H2 rho G A. A is the circular area. I mean, projected area. We call it projected circular area. H2 rho G A. What is F1 here? H1 rho G A. Okay. Now the liquid is moving with an acceleration A. Here we can apply F equal ma for this particle, liquid particle or the water particle. F2 minus F1 equal mass into A. Keep it there. Right? Keep it there. Now I should consider a coke which having the same volume but different mass. Now the mass is less or more than the m. If it is a coke, less or more, less, exactly less. It is m dash, right? At the same position, if it is the same position, the same forces are applied F1 and F2, isn't it? If that is the same position, F1 and F2, same forces are applied, isn't it? Right. If the same forces are applied, if the system is taken with an acceleration, each and every particle in the system should maintain the same acceleration. Now you are inside the bus. The bus is moving with 20 ms minus 2. So do you have a different acceleration? No, you don't have a different acceleration unless you are dancing inside it. Different same acceleration must be maintained, isn't it? So the same thing is there. Even though it's a coke, it should maintain the same acceleration. Let's apply F equal ma for the coke, right? For the coke. F equal ma. When you apply F equal ma, F2 minus F1, m dash A. m dash a. Now you will realize m dash is less than m. Actually, m is greater than m dash. Here, this part is low. So that means this must be small. There must be a kind of force. I mean, there must be kind of force. Subtract that value, then only you can say the same acceleration is maintaining. To subtract that, what happened? To subtract that, what need to be there, this scope must be placed like that. So what happened? The tension component develop their tension. Let's say this angle is theta, t cos theta, t f2 minus f1, t cos theta equal to ma dash. T cos theta give the required reduction in the force. Did you get my point? So the string should be angle or the position as this, then only it happen. Right? I explained the theory section under that. Right? I haven't done this question inside the class, but I have done some part of that. But I think it's better to have a small note related to that, because these are rather confusing questions for the most of the students. So better to have a small idea about this. Let's try this subtopic. The fluids which are accelerating horizontally, the fluid which are accelerating horizontally. Fluids which are accelerating horizontally. Right. Right. Let's consider a vessel. Let's consider a vessel filled with water. Filled with water. Number A. Number A. If the vessel is number A, if the vessel is taken, if the vessel is taken, if the vessel is taken, if the vessel is taken horizontally, if the vessel is taken horizontally with constant velocity, or if it remain rest, the liquid interface or liquid surface, simply the water surface, is exactly horizontal. Exactly horizontal. Right. Please draw that. Don't take much time. Draw that. This one. Right. Next point, number B. Now let us consider. The liquid vessel is taken with an acceleration. Liquid vessel is taken with an acceleration towards the left. Towards the left. Towards the left. So the water interface placed as in the following figure. Placed as in the following figure. Or position as in the following figure. Position as in the following figure. Okay, next. Draw that, right? Number C. Let us consider water particle of mass m, volume V. Draw that, mark these values. and come to that F2 minus F1 equal MA. F2 minus F1 equal MA. Okay, right. I think you have come to that F2 minus F1 equal MA, right? Okay. Number D. Let us consider piece of cork of mass M dash, which having the same dimensions, which having the same dimension as the water particle, within bracket, right? M dash is less than M dash is less than N. Draw that, come to this point, right? Come to this point. Have you come to this point? Yes, the Asma, what you're asking me is correct. There must be a force because it should accelerate towards the left. No, there must be a resultant force. Right? There must be a resultant force. That's why it accelerates. Otherwise, it is not accelerating. No. Right. Here, to maintain the same acceleration as the water particle, the resultant force need to be less than this value. Therefore, if you place with the string, string make an angle like this. This is how the water surface is there. This is how the object is placed. Cork, right? Piece of cork is placed like that. Right under that, to maintain the same acceleration as the system, 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 resultant force need to be reduced. For that purpose, tension force, component of the tension force helps, component of the tension force helps to give the same acceleration. Now it is okay. The same acceleration can maintain. Otherwise, you can't keep the same acceleration. So what happens if the spring is not there? Definitely, it comes to this location, or else it comes to this point, and because it's touching surfaces, the normal reaction would apply there. Understood? If the coke, that would happen. Better write this one also. This is a liquid vessel, right? The piece of coke is connected to a string, and a stone is connected to a string, and you all are taking the system with an acceleration, right? So I try to give this figure how these objects are positioned if the system is taken with an acceleration. Coke is like this. It is one that we normally not observe. The coke appears like that. Piece of coke appears like that, right? It is not appear. It is the way that it positioned. But piece of stone is definitely like this. If I take with an acceleration, you will realize it comes to that. Neither. You better draw that both figures. Then it's easy for you to understand the balance sections. Always remember, if the object density is less than the density of the medium, if the object density is less than the density of the medium that it plays, it do unusual thing. That is the unusual thing. If the density is more than that, more than the mean, actually density of the coke is less than the density of water. Density of the stone is more than the density of air. This is air. So it behaves as normal thing. It is unusual thing. Please draw that. Let's say we have a car. The car is accelerating. Car is accelerating towards that direction. The car is accelerating towards that direction. So you have a hydrogen balloon in your hand. If you place a hydrogen balloon, let's say it is connected to the roof of the car, what we could observe, we wanted it to be like this, but it never happened. Instead of that, it is there. It position as this. Understood? Why? Why? What is the reason? The reason is it has less density than the air, hydrogen balloon. Okay? Let's say hydrogen, right? H2. not the component of the weight asma, it is the component of the tension. We have a stone, the component of the tension, theta, T cos theta helps to give the required force for the acceleration. Otherwise, if you keep an object like that, stone like that, when the system is accelerating, there is no force for that, no, to accelerate. In order to give an acceleration, it should be slant like that. Make an angle. I will draw this one also for you to get an idea. The liquid vessel is rotating. When the liquid vessel is rotating, it appears to be like that. And the piece of cork is connected to a spring and it is connected to the bottom. But we could see that it's slanted like this. Actually, we thought that it is like that, it is inside the water. We feel that it is inside the water, and we feel that the required tension provides the required centripetal force to move in a circle. No, it is not the case. Either of that, it position like this, and it moves in this circle. The reason is it has a less density. Okay, draw that. Question number 16. Actually, I have done the similar type of question earlier also. Question number 16. In the diagram, AB is a thin uniform rod made of a material of density rho, freely hinged at point A to the wall of a vessel containing a liquid of density sigma. Density sigma. It is the hinge. When the equilibrium of 1/5 of the rod is projected outside the liquid, the ratio of the density rho over sigma is, this is rho and that is sigma. 1/5 of the total volume, so that is L. If so, that must be 4L. Here we have an upthrust, it is U. It is U, and this must be definitely 2L, because from here to there we have 4L. L, 4L, that means 2L. Here we have the weight, which is mg. From this point to that point, we have 2.5L. 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 So now you can take the moment about point A, sigma 2 about point A in that direction equals 0. I'm not referring to the cos theta values because it's not required. Next cancel. Mg into 2.5L equal U into 2L. L cancel. The mass, volume into density, cross section is A. Total length is 5L. Total length is 5L. Volume sigma G into 2.5 equal upthrust. Volume A into 4L. Volume rho G into 2 into 2. ALG cancel. Here we have 5 sigma, or the like 5 into 2.5 sigma, that is 8 rho. 8 rho. That is how much? We can say that 12.5 sigma 8 rho. What they want? Rho over sigma, rho over sigma. Sigma 12.5 over 8. Or else we can say Did I make a mistake? Density of the liquid is no, it's wrong. The liquid is not rho, it is sigma. Liquid is sigma, not rho. I make a small mistake. This is sigma. This must be rho. This is sigma, and that must be rho. Here we want rho over sigma. It is 8 over 12.5. It is 16 over 25. First one is the answer. Question number 17. Figure shows how cross-section of three hollow objects, two of which have opening closed and soft rubber are another without an opening just floating inside the three bottles of water labeled A, B, and C. When the excess pressure is applied to the air above the water surface in all the three bottles, bars in their mouth hands. Right. Let us discuss. So in this particular case, if you apply certain pressure, right, due to the Pascal's principle, we know that that pressure is go through the liquid without any drop, right? Do you remember that? It travel through the liquid without any drop. Even it is common for this one, and the another one. I didn't draw that. I don't want it to draw. The same thing would happen. Here, there is no resultant because of that force, because of that pressure difference. I mean, there are some kind of extra pressure. No, there is an extra pressure. That extra pressure apply every location. So no resultant because of that. The pressure is applied only. But there is something happen here. There's something happen here. Now it is floating. This is also floating. When you apply extra pressure, this is the rubber membrane. When there is an extra pressure, there is a volume change there. What happened? There is a huge pressure to this rubber membrane, so the volume reduce. Volume reduce, that means it become like this, isn't it? Volume reduce. Now it was floating. The upthrust reduce. Upthrust reduce means going down. Understood? Right? Upthrust reduce, going down. So that's the answer for that question. Fourth one, look at that. Move down, remain stationary. C remains stationary while the other twos are moving down. Okay. Let's move to question number 18. So that's why I told you this is somewhat important points under the fluid static, because most of the students, you don't get that chance to discuss this much of MCQ. So get the benefit of it, right? Get the benefit of it. Question number 18. A vessel contains oil and mercury. A metal sphere float in the interface with one half of its volume immersed and mercury and other half of the oil. The density of the metal is. This is V by 2. This is also V by 2. The similar type of question as we discussed earlier. U1, U2 must be equal to the weight of that. U1 plus U2 must be equal to the mg. U1 V by 2 rho oil into J plus V by 2 rho mercury into J. Mg means V, let's say V is the volume of that, sigma G, V sigma G, density of the material. V cancel, G cancel, rho oil that is 800 divided by 2, rho mercury 13,600 divided by 2 equal sigma 400 plus 6, 8, sigma. What is that? 7,200. Sigma is that. 7,200 is the density of that metal. Question number 19. A crown of mass 1.4 kg has an apparent weight of 1.3 kg when submerged fully in water. A crown of mass 1.4 kg has an apparent weight 1.3 kg when submerged fully in water. The mean density of the material of the crown is, right? Do you remember an equation which I discussed? What is that? Relative density. Relative density equal actual weight divided by actual weight minus apparent weight. Actual weight minus apparent weight is the upthrust. So this equation again can be divided like this: actual weight divided by the upthrust. Actual weight is given. It is 14 Newton. Let's say 1.4 kg. Actual weight is 1.5. Apparent is 1.3. It is a relative density. 1.4, that means let's say 14, no, let's say 1.4 divided by 0.1. Relative density equals that. So let's say the density of the material as sigma divided by 10 to the power 3, sigma equal 14 10 to the power 3 kg per cubic meter. So look at this. If you know the theory, that also very easily we can get the answer. So it helps you to get the answers very easily. Question number 20. A tube of length L is fitted to a vessel having a height L and bottom of area A as shown in the figure. If the internal area of cross section of the tube is A and the vessel of the tube is completely filled with the liquid of density rho, the force acting on the bottom of the vessel by the liquid is the force applied on the bottom of the liquid. What is the pressure here? Pressure is equal to L plus capital L rho G. That is the pressure here. How to find the force? Just multiplied by the area. That's all. Neither. First one is the answer. Pressure always gives from the open space. From there, we get the total height L plus capital L. Okay. Let's move to 21. Right. A cylindrical metal vessel having thin wall of height 4h contain water up to height h. When immersed in water, the cylinder floats with half of its height below the water surface as shown. If the cylinder is to be floated with its almost entire height underwater, the water level inside the cylinder has to be raised h. Raised, what is the value? That's what they want you to find. So now this must be the appearance. Right? This must be what kind of a value, that is what they asked from you. Right. I will explain this. Look at here. When this kept like this is water. This is water. So water, the weight of the system is given by the vessel weight plus the water weight. I mean the water weight W1, the vessel weight W. Right? So there's an upthrust on it. There's an upthrust on it. So simply the upthrust on the vessel is equal to this particular volume. Are you clear with that? Are you clear with that? The upthrust on the vessel must be given by this volume only. Right? Because this is water. We don't want to think about that. Water has equal upthrust, so don't need to think about that. Weight of that is equal to the weight of the water. So this volume is important. This volume provides the upthrust on the vessel. Total weight is balanced by that upthrust. Right? So when this is immersed, we need to make sure this must be H. Why? That need to be there to balance the weight of the vessel. Can you understand that? Since the vessel itself is 4H, this need to be raised up to 3H. I'm just very simple questions. If you go with the very, I mean, it has to be with the logic, otherwise difficult. This must be, you need to remain this portion to balance the weight of the vessel. If you fill with that part, what happens? It definitely immerse. Because there is no upthrust to balance the weight of the vessel. Fourth one is the answer for that. Let's move to question number 22. Question number 22. A beaker of water is kept on a compression balance. At T equals 0, a solid object immersed just beneath the water level, as shown in the figure, is lowered slowly into the beaker until it rests bottom. The variation of the reading S of the balance with the time T is best represented by. Right. The reading here with the time. From when you take this instant, the reading is given by two things. One is the weight of this vessel plus water plus the upthrust of it. The upthrust, there is upthrust on it now. The same upthrust on the liquid also. There is upthrust on the liquid. So it will last until it touches the bottom. When it touches the bottom, what kind of a thing would be the reading? The weight of that plus the weight of the object. Right? So definitely that value would be large. First one is the answer. Okay? Right. I will tell you a small thing. The same system, right? Same system. Only thing is, I started from there. How we get the answers. I will start from there, the reading. At this point, the reading only tells you W. You have a W. When it is now inside the system, we get W plus U. More than that, no. When it is touched with the bottom, what we have W plus mg, which is more than the upthrust. Understood? That is how it happened. Okay. Take your pencil and write this on that. In the next year, they would ask that question. Don't know exactly. Question number 23. Uniform solid cylinder of weight 6 Newton is floating vertically in a liquid with 1/4 of its height above the liquid surface. The minimum vertical force required to immerse the cylinder fully in the liquid is. The total weight of that would be 6 Newton. The upthrust is there. If I simply tells you, that means only the 1/4 of the volume is on top of the liquid surface. That means 3/4. This much of volume is inside it. That is because of 6 Newton. For each and every 2 Newton is responsible for this particular portion. The next 2 Newton is responsible for that to immerse. Then this portion needs to be responsible. If you want to immerse the next portion, what kind of a weight I should put in on it? Put on it. What is that weight? 2 Newton. We can do this question in a mathematical way, but I don't expect you to do that. Think logically. Get the answer within 1 or 2 seconds. That will help you to do the rest of the questions properly. Right? Let's move to question number 24. 24. A rocket carries 1.8 10 to the power 4 kg of liquid oxygen in a vertical tank of cross section 3 square meter. 3 square meter. At the lift off, the rocket accelerates vertically 2 ms minus 2. Related to the earth, pressure on the bottom of the tank at the lift off. Let's say this H, the tank is fully filled with liquid oxygen. The mass of that is given 1.8 10 to the power 4 kg. Right? Right. Let's say the height of the the tank. I mean, tank is h. So you can say that ah, A is the cross section, Ah rho oxygen G must be equal to 1.8 10 to the power 4 into 10 G. Ah rho, let's say rho G must be equal to 1.8 10 to the power 5. Or else you can cancel 10 and 10. H rho value equal 1.8 10 to the power 4 divided by 3 because it's a 0.6 then 10 to the power 4. 0.6 10 to the power 4 is the answer for the H rho value. 0.6 into 10 to the power 4 is the H rho value. Right. Now the pressure is given by H rho G plus A. Do you remember I told you G effective? H rho G effective. When it is moving up, we get to take G plus A, G effective. Right? H rho is given by this answer because it is not given anywhere else. We have to find it with the data given. 10 plus 2. That means 12 now. 12 into 6 means 7.2, 10 to the power 4 Pascal. Newton per meter square. That means fifth one is the answer. Do you remember I told you during our discussion, the liquid height difference must be maintained. Height difference must be maintained. If the system is taken towards the horizontal direction with an acceleration, this is h. Let's say the acceleration is a. If the difference between the two locations is L, what was the answer I told you? H must be equal to what? Do you remember the MCQ style I told you? Don't you remember that? Don't you remember anyone else? I told you to remember LA over G. That is the height difference. But let me to show you how it comes. That's also important. Let me to take a liquid particle on the liquid surface. Now it is moving with an acceleration. Let us consider a liquid particle on the liquid surface, right? Here, the weight of that would be applied. This is a normal reaction which is developed because of the other rest of the particles. Here, this angle is theta. If that is theta, you can say this is theta. This is theta, and that must be 90 minus theta. This is 90 minus theta then. Okay. Then this must be theta. Understood? Yes or no? I consider the liquid particle which is on the liquid surface. So there must be a kind of reaction force on the rest of the particles. This is theta, then this is theta. It is perpendicular line, 90 minus theta, then this is theta. Here, horizontally, there is an acceleration. F equal ma, we can apply. R sine theta must be equal to ma, number one. Vertically, R cos theta, R cos theta, R cos theta, this is R sine theta, must be equal to mg. Balance the weight of that particle. 1 by 2, R cancel, tan theta equal A over J. Tan theta equal A over J. Okay. So for the time being, just keep it there. Tan theta equal A over G. If you take a system like that, this also should maintain the same angle, isn't it? It should also maintain the same angle, isn't it? Yes or no? It should maintain the same angle, yes, regardless of this water surface. It should maintain the same angle, right? Therefore, if you take tan theta here, tan theta equal as per this derivation A over G, and also tan theta equal H divided by L. This is L, no? H divided by L, A over G. So H equal AL divided by G. So remember, that's why I asked you to remember AL over G is there. So if you know those sections, hydrostatic is not difficult. So I discuss most difficult hydrostatic 25 questions. I discuss each and every questions without skipping any questions. I hope that is more than enough to understand the balance. So please do again those 25 questions to make it much clearer. Try yourself. Maybe you won't be able to. You didn't get the exact answer when you do it by yourself. When you do it, you don't get the exact answer. But we discuss it now. You can try those, right? So please try that. And that's all for today. We will meet again on next class, live class. I mean, we will continue the fluid dynamics also we need to complete. Oscillation waves, simple harmonic motion we all are going. We will do that part in the coming week also. Right? You have anything to ask? Do you have anything to ask?